Good morning. Today class we are going to discuss propagation and propagation models. Why that is so much important in cellular communication. Not only cellular communication, in wireless communication. First, we should see what is a propagation. Now let us have one example. You have a transmitter, you have a receiver. Normally throughout the propagation model study, we are going to always consider that the transmitter, the height of the transmitter antenna is in a higher position. It's an assumption, and this one is the height of the receiver. So now the purpose of this propagation is that our propagation model, it is used to study or mathematically used to study how much this radio waves that is being emitted from the transmitter can reach up to a particular point without distraction or without losses. So this is the purpose of this propagation model. So it is a, in other words, it's a mathematical study or experimental study by which the waves, the maximum transmission range of the wave, the propagation model. So by default, what are the issues that affects the propagation is number one is absorption. Absorption. Number two, it is reflection. Number three, it is scattering. Number four, it's diffraction. So in this series of lecture, we are going to discuss how a propagation model is going to be defined, and this propagation model incorporates these things: absorption, reflection, scattering, and the diffraction phenomena. So due to this phenomena, your propagation, that your electromagnetic wave can't be able to transmit the large distance. Absorption, normally absorption in the sense that the medium, for example, in this case, you are transmitted from a point A and your receiver is point B. Between transmitter and A, the medium is a thick vegetation area. Okay, thick vegetation area. So here, the absorption, this electromagnetic wave, the rate of absorption varies with respect to what kind of floor we are using. Suppose it is an indoor, the absorption will vary. And what kind of material you are using. Suppose if you are indoor, you are having a tiles. So your propagation will also, absorption will also vary. Suppose you are using marble, you are using ordinary floor, and this absorption is very depend upon what kind of floor medium. So what are the medium that is passing from the transmitter to receiver, the medium that absorbs electromagnetic wave, this phenomena you term as absorption. Second one is reflection. As you know that electromagnetic wave, when the electromagnetic wave hits a conductor, the possibility of the electromagnetic wave get reflected. So there's a second phenomena is called reflection. Reflection phenomena occurs when this electromagnetic wave is being hit by an object, it started with reflect. So it is called reflection. And scattering is similar to reflection. One difference is that when the electromagnetic wave hits the object having the lower wavelength, that's for example, it is a sharp edge object. So instead of reflection, it started to scatter. It means that this will point act as a secondary source. This is called scattering. The third phenomenon is called scattering. The fourth phenomenon is called diffraction. Diffraction is a phenomena whenever this electromagnetic wave hits an object. For example, let us take a glass medium. So it will start penetrate in the sense that some of the component will get reflected, some will get passed through this, and this one in terms of this phenomena is called the diffraction. Because of these four phenomena, there might be losses in the propagation. So we are going to study how the propagation losses occurs, and these are the four phenomena that are the causes for the propagation. And we need to build a model to study how these propagations are loss or maximum path loss of your electromagnetic waves or radiated waves. So the first model we are going to discuss is called free space propagation loss model. So the purpose of study is that the impact of this phenomena affecting the propagation. What are the phenomena? Absorption, scattering, diffraction, reflection. This phenomena affect the propagation, wave propagation, and we are going to build a model to study the propagation laws or the path laws. Now, for the first model is called free space propagation model. Free space, or it's called free transmission formula. Free space propagation model. So in the free space propagation model, how it will do in the sense that it will assume the coverage area as a spherical shape. Okay. And the center point, the midpoint, and this one is the radius R. And R it is other is called the center point. We are placing a cell phone tower or any antenna. Okay. And the receiver might be at any point of this one. And this one is called as a distance between the transmitter and receiver. And I think it is clearly visible from this diagram. Here the D represents the distance between the transmitter and the receiver. Now here, how we are going to measure this call? First we have to measure the received power. So the formula is that received power PR is equal to PT GT. GT means gain of the transmitter, and A is the area divided by 4 pi D. What is that 4 pi? As you know, the area of a sphere is 4 pi R square. Or here instead of R, we are having a D. So this 4 pi R means 4 pi D square. Okay. So this formula comes, that 4 pi D comes from the area of the sphere. As I mentioned that you have to imagine this area not as a circular pattern, as a sphere. So PR equal to PT GT A divided by 4 pi D square. So 4 pi D square is the area of the sphere, or it is in traditionally we study 4 pi R square. Here instead of R we are just having that D. Notation is D. Now area. So we need to change this. What is that area? So here A. So A means that here it is not an area. So A means that the particular object, or this one, that receiver is called A. So now how we can derive the A, or A equal to GR. Okay. So here A is the point where the receiver is being there. Okay. So it is GR. So as it is the gain of a receiving antenna divided by 4 pi here into lambda square. Okay. It means the wavelength. Okay. So this is the A. So here A represents the point of the reception. Okay. The point of the reception area, and here the 4 pi D square means the area of the sphere. And now we are substitute, this is considered as equation 1, this is equation 2. Substitute equation 2 in 1, your equation becomes, one more thing is that into L. So here L represents system loss. System loss in the sense that, for example, your receiver is here. Your receiver, you assign the receiver as MS. MS means mobile station, your mobile phone. This mobile phone will lose the signal because of some configuration issues, as well as some heat generated in the phone. So that the loss occur due to the devices is called system loss. So normally the value of L is always 1. So this equation can be rewritten A equal to GR, gain of the receiving antenna, lambda square divided by 4 pi. Okay, here the value of L is 1. What is L? L is a system loss. System loss is the loss associated with the mobile station. It means that due to heat, some of the radiated power or some of the radiated energy might not be properly received, or it might be lost due to that thing. So this is called system loss. Now substituting this equation number 3 in equation number 1. So the equation became PR equal to PT means transmitted power, GT, GR into lambda square divided by, already 4 pi is there, here also 4 pi. So it became 4 pi D the whole square. So this is the equation for. So now the path loss equation is given by path loss equal to 20 log PT by PR. Now what we had to do is that we had to rearrange the equation number 4 in this form Pt by Pr. So I am rearranging. So what will happen in the sense that when it is Pt by Pr, okay, right? So it will become 4 pi the d the whole square divided by Gt Gr, then you have one thing called lambda square. So what happens here is that now the value of Gt, gain of a transmitting antenna, and the gain of the receiving antenna is always considered as a 100%. So it is 1. So find the equation number 6 can be rearranged in this fashion. Okay, Pt by Pr is equal to 4 pi d the whole square divided by lambda square. Now what we are going to do is that we are going to substitute equation number 7. Equation number 7 in equation number 5. So when we substitute the equation number 7 in equation number 5, path loss, for our simplicity I am just denoting path loss as PL in terms of dB is equal to 20 log this value 4 pi d divided by lambda the whole square. Okay. So now you know logarithmic notation, you can bring the square here. So the equation will become is 40 log 4 pi the d by lambda. So this is the equation for deriving path loss using a free space. So in this series of lecture, first we are going to discuss something about free space propagation model. The free space propagation model always consider that's a line of sight between propagation between transmitter antenna and the receiver antenna. Now this free space model is used to calculate the losses encountered between the transmitter, or it otherwise give how far your energy has been radiated or how much distance your energy has been radiated. For that we are using this equation. Let us quickly summarize what we have discussed. We have seen one thing called the formula is that the received power PR. We consider the coverage area of the transmitter in a spherical form. So spherical form means that area of the sphere formula is equal to 4 pi r square. So instead of r, I am just replacing r with the d. Here the d is the distance between the transmitter and the receiver. So this equation became 4 pi the d square, and received power equal to transmitting power multiplied gain of the transmitter in the A. Here A represents the transmitter location, not area, it's a transmitter. So this A is given by what? A is a receiver thing. So it is GR, gain of the receiver, multiplied by lambda square divided by 4 pi. Now substitute equation 2 in equation 1. Okay, right? So your equation 1 will become this fashion. Okay. So meantime, we just want to know that there's one thing called L. Here L represents system loss. System loss in the sense the loss associated with your mobile station. So due to the heat energy produced by the mobile station, there are some losses are there. This loss is called as a system loss. Normally the system loss value is 1. So L equal to 1. So when we substitute L equal to 1, this equation will be reduced to this form. A equal to gain of the receiving antenna lambda square divided by 4 pi. When you substitute this value, equation 3 in equation 1, the equation 1 will become like this. PR equal to PT, that is transmitted power, gain of the transmitting and receiving antenna, its wavelength divided by 4 pi the d the whole square. Now the path loss is given by this equation. Path loss equal to 20 log PT by PR. Now we are rearranging PT and PR in the equation and substituting here. And one modification we are doing is that in this equation we are making the gain of the transmitting antenna, gain of the receiving antenna unity. Finally, the equation will be in this form, in the logarithmic form. So this is the final equation, path loss final equation. So this path loss study is used to measure how far the signal has been transmitted in a line of sight condition. However, this study has been overcome by a second propagation mechanism. This is called two-ray mechanism. Now, in the next series, what we are going to do is that we are going to show how we can study path laws practically. So we have a tool called Network Simulator NS3. I think you are familiar with most people are familiar with NS3. Or those who are working in the area of wireless domain, they might know that NS3. So using NS3, NS3 is an emulator where you can able to do a lot of emulations. It means that you can connect your machines in a real world environment, and it can also act as a simulator. So we are going to demonstrate how this propagation laws impact the throughput of a data. So in the next lecture, we are going to show that how this different propagation model have an impact on the data throughput. That is, we are going to study the TCP. We are going to transmit the data between a sender and receiver in a wireless setup. We are using a propagation loss model, and we are going to see what's our throughput, what's the latency occur between the transmitter and receiver under line of sight condition as well as in non-line of sight condition. For that, we are going to use two different mobility models. One is Manhattan mobility model, other one is the traditional two-ray ground model, or one thing called nomadic model. So RPGM model. So this model should be developed by a bone motion mobility model. From that, we are going to port into NS3. So in the next video, I am going to show how this propagation model we can study using NS3. NS3 is a beautiful simulator. So in the next series, so in the next video, we are going to see how the Freespace propagation model are going to be have an impact on the network throughput or the data throughput. Okay, thank you. Thanks for watching.